So this question is called Adamat. In this question, what do you have to do is, suppose you have a matrix which is of size n into n. So it will be something like this: 1 2 3 4 5 6 7 8 9 10 11. Suppose you have this matrix, and now you have just shuffled it somehow. So this matrix has been shuffled. So the numbers will be from 1 to n square, but they will be shuffled, right? So now what you have to do is, basically you want to sort this matrix. So basically, if it was shuffled, like it has numbers from 1 to 16, but it is not like 1, there should be 1 2, then there should be 3, right? But it is 9, so some of those are shuffled. So you have to sort it, or you have to make it in this way, that it is 1 2 3 4 5 6 7 8, right? So that is what we have to do. And you are given one operation, and you can perform only that operation. So what is that operation? That operation is, you choose an integer L which will be less than n, and we are talking in one based. So in one based indexing, it can be equal to n as well, and transpose the submatrix between rows 1 and L and columns 1 and L. For example, if you choose L is equal to 2, then you will be transposing this matrix 1 2 5 6, right? So something like that. So for choosing one L, this is the operation, right? So that's it. So you're given an initial state, and you have to tell the smallest number of operations required to sort the matrix, right? So this is what we have to do. So the operation is transposing a submatrix starting at the top left, and it will just transpose it, and you have to find minimum number of such moves, right? So let's look at this thing. So suppose you choose any submatrix, right? So suppose you are choosing this submatrix, let's say this. So you will basically rotate. So if you imagine this diagram of elements here, then basically when you transpose, you rotate around this axis. So basically this element will become this element, this element will become this element, this element will become this element, right? So that is what we want to do. So this is one operation which is possible, right? But so if you think about that, so this is how it will happen. So you can transpose this element to here, transpose this element to here, something like that. But you should notice that you can't actually exchange these two numbers. So these two numbers in circle, right? Given the operation we have, we can never exchange these two numbers. So if this was the case, we will never be able to solve it, right? But it is given that it will always be possible. The initial state of matrix is chosen in such a way that it is possible to sort it. All right, so this is the assumption. So basically it will never be the case. So what you should know is that whenever you perform that operation, if you're fixing any one of the number in this row, so if you look in the original diagram, it will be this way, right, diagonally. So if you fix any of the number in this row, all others should get fixed, right? Because if you can't do something like this, that I want to exchange these two, but I don't want to exchange these two, all will be flipped when you're doing transpose. So that is one observation, that you are flipping the whole diagonal. So if you are talking about this side of diagonal, which is pointing towards top right, then you flip the whole diagonal at once. So ultimately what is happening here is, if you're flipping the whole diagonal at once, so every diagonal can be associated with a state which will say, is I am in the correct orientation or not. For example, if we look at, so the first element will always be correct because you can't do anything with it, right? So because if the solution is possible, then it has to be correct. But if you look at 2 and 5, then we can just say that it is in correct orientation, because second element has to be 2. So 5 will always be there because there is no other way that it will be valid. So 2 and 5 will always be there if 2 is there. So if you look at third one, which had to be 3, right? So that is not matching. So if 3 is not matching, then here it should also not match. So we can associate with this diagonal that it is not set correctly. So we can say this is true, this is true, this is false, or this is 1, this is 1, this is 0, something like that. So for each diagonal, I'm saying that whether it is set to correct orientation or not. So it can be true, false, it can be anything, right? How do I figure out if it is not in correct orientation? I can match any of the numbers. So if I'm looking at, let's say, this diagonal, I can match either this or either this. If any of them is not matching, then it is not in the correct orientation. If it is matching, then it is in the correct orientation. That's it. So now I have changed this problem when I'm looking in this direction, that we have some diagonals, and each diagonal can be represented as 1 0 1 0 0 1, so something like that, where 1 will say that yes, I am in correct orientation, and 0 will say no, I am not in correct orientation. And now, how will the operation? What will be the operation for this binary number, right, or binary string? So in one operation, what you were able to do is choose mm, any of the. All right. So you will actually start from so yeah. So it's an implementation bit detail, but you want to start from this second diagonal, because first diagonal you can't change, and last diagonal also you can't change this one, this element and this element. So you start from this. So in this case, your orientation will be orientation matrix will be 2 is correct. So this is true, 9 is false. So similarly, right, for example, now you go in this diagonal, 13 is wrong, so this will be false. Then 14 is also wrong, which will be false. 15 is also wrong, which will be false, and so something like that. So you have to make that thing for all of your diagonal, and let that convert to one, something like this. This is happening like you can implement it this way also, but you need to understand that we are transforming this problem to that orientation of each diagonal is either correctly oriented or currently oriented, or not correctly oriented, right? So now what how will our operation transform? So look at this thing. So when you are transforming this, you're flipping all of them. So if this was correct, it will actually become incorrect. If this was correct, it will actually become incorrect. Okay, so something like that, right? Okay. So now what we can do is so because it is given that it will always be solvable, what we can do is like we can start from the end. And so like now the problem changes. So because it is flipping everything, so either it will, so when it is flipping, either it will make it correct or either it will make it wrong, right? So how does that happen is basically, if you convert it to this binary string problem, you will say that I can choose an starting index and ending index, and I can flip all bits. Why? Because if it was correct, it will become incorrect, and so you can look here as well. So if it was correct, it will become incorrect, and if it was incorrect, it will become correct. So that's what will happen in one move. So basically you have a move, you have, so the problem changes to, you have a bit string, and you have a move which will flip all the bit string starting from 0 to some length. And using how many operations can you flip these all to 1 or flip these all to 0? So if you are saying that 1 is correct orientation, how many operations we need to flip all to 1, right? So this is the problem ultimately. How do we make this matrices? You can iterate over these elements, right? Because if any one of them is incorrect, that means that whole row is wrong orientation. So now, so this is so how do you solve this problem is, like, you start from the last 0. We will do a greedy thing, but we need to take care of something. So basically last 0 has to be fixed. So we'll start from last 0. So let's take a smaller example. Let's say 1 0 1 0. So if you take last 0 and you flip it, it will become 0 1 0 1. So last one is solved, but the earlier ones are not solved now, right? So this is the only thing which we need to take care about is we need to remember how many operations we have done, so that we know if it was originally correct. So suppose originally it was 1 and we have done even number of operations after it, right? Then it will still be 1. And if we have done odd number of operations after it, for example in this case we have done only one operation, then it becomes 0. Then we have to fix this as well. So now we'll have to do an operation here, but in original case it was correct, right? But because we shift fixed this, now this has become bad. So that is it. So if you think about it, you should be able to understand what is happening, that you fix one, then you go towards left side and you just try to figure out if this is currently fixed or not. So implementation is like, you have expected number at a particular column and a row. So I'm iterating over, I think either I'm iterating over this one or either I am iterating over this one. In this diagram it will either be this one or either be this one. So I'm iterating from opposite side and I'm checking if it is not equal to, if it is equal to expected or not, right? So now think about this. So it can also happen that originally something was correct, right? Yeah, I mentioned that. So if something was correct and then it got flipped, so that is a case we have to handle. So if current was equal to expect, not equal to expected, that means orientation is wrong currently. Originally the orientation was wrong, and so if used means we have used one flip. So basically used means the parity of the flip we have done, number of flips we have done. So if it is false, that means we have not flipped anything, or we have flipped it even times. That means this condition is true and you can increase one answer. And else it was opposite. So suppose now uh, we know the orientation is correct, but we have used a flip after it, or we have used odd number of flips, right? Then we have to increase the answer, something like that. So basically what I'm saying is, when I come here, although I know that it is equal to expected, current value is equal to expected, but as I have used a flip already, then I need to increase the answer. I have to do one more flip. So something like that. So think about this problem, that how will you do this problem, converting all to one, and then you can just look at this code and hopefully it will make sense. Thank you.